all, thank you everyone for being here and, in person and all that. I'm still getting used to in-person conferences. It's been an extremely long time since I did my last one. As an example, I got my hair done to look extra good here on stage. And then last night it was pouring rain and the whole thing looks the way it does today. I had no idea it rains. In California, it certainly does not rain, and it was very unexpected. So getting used to travel. In my previous life, when I was still traveling and giving talks, I gave a talk in QCon San Francisco in 2018, and it was about the evolution of microservices, and the last part was the future of microservices. And I said that, hey, serverless looks like an interesting step in evolution, and you have all those functions, which are very small serverless, but it's not clear how all those functions can interact with databases. Where do they store data? How do they set their state? Things were extremely unclear. And when you looked around and like, okay, which were serverless databases to match those serverless functions, it was like, well, we don't really have many of them. There was basically Amazon DynamoDB, and there was Amazon DynamoDB. Snowflake was technically serverless in some respects back then, but nobody thought of it as serverless, and then there weren't really a lot of other options. Fast forward to today, I only fit a partial list into this slide, but obviously there is a lot of systems that say, hey, we're a serverless database, we were built for serverless workloads, we're a database for the cloud. All those things are now all over the place. So obviously, in the last 5 years, except other than a pandemic, other stuff has changed as well. So why is that? Why did we go from almost no serverless databases to now we have a lot of them? Well, the cynical answer is to say it's a buzzword. Anyone who can put serverless in front of whatever they're doing goes and puts serverless in front of whatever they're doing. This is not incorrect, but I think there is a lot more to it than that. And this presentation will basically go through the reasons that serverless is happening right now. And we'll start with one reason we have serverless right now is because we can. We are getting better at distributed systems. We have better guarantees, better algorithms, better foundations. We learned how to tame a lot of the issues that really made distributed databases a serious challenge even just 5 years ago. And we're going to talk in detail about those different architectures that make serverless databases possible. The other side is because it's worth it, because there is now a lot of workloads that actually benefit from running on a serverless database as opposed to something a bit more traditional. And I'm going to talk about in what cases is it worth it, and in what cases you should just stay exactly where you are and nothing changed for you. And the last point is because serverless in the form of function as a service is a big deal. Those are new workloads. They do have fundamentally different requirements, and they do need data somewhere. So we'll talk about what the force that function as a service applied toward our data architectures, and I'll give some examples of data architectures that I think are particularly good for serverless functions. Okay, so let's start talking a bit about you guys. You look a bit like that. You're at QCon, so I can assume all of you are very senior engineers and architects. I do not assume that all of you are building databases. Now, I'm going to spend about half the talk talking about the internals of a bunch of serverless databases. Why am I going to tell you how to build a serverless database when clearly the vast majority of you are not going to go back and tell your boss, hey, I'm building a serverless database now? Well, I think you guys are in a position to choose the technologies for yourself, for your teams, for your companies. This is what senior developers and architects do. And I think knowing and understanding the internals and the trade-offs that were involved in creating those systems will allow you to make really good choices. So this is the goal, to equip you in making good choices. If people here listening to my talk would say, until today I thought that serverless is marketing BS, but now that I understand really what's going on and the trade-offs and the benefits, I think I may look a bit more into it. If that's what you say then, I've done my job. Now, about me. Until about a year and a half ago, I was leading Cloud Native Kafka for Confluent. I led this team of amazing engineers, and our goal was to build, well, serverless Kafka experience for Confluent Cloud. And when we said that we want serverless Kafka experience, and by the way, Confluent marketing was very responsible. They never said serverless. We only said that internally. But it was our vision that our users will only give us their workload and the credit card. And that's it. We will take care of everything else. You need more resources, you need something optimized, you need to move partition around, you need a different configuration. Don't worry about it. Send us, produce, consume, send us data. We will figure out the rest. So when I say serverless, this is my mental model. Now, as a vendor, it obviously meant that there was a lot on for us. The usual, we have to be highly available, we had to never lose anyone's data, and then we had to provide elasticity. Because they're giving us a workload, we don't know how much of it will be and when it will show up. So we need to be able to scale clusters up and down, but it's even more than just auto-scale. Elasticity for me means being able to resolve hotspots, resolve noisy neighbors, really making sure that every part of the workload always has optimal performance at all times. So it was a lot of smart people investing a lot in this. Now, fast forward a year and a half later, I'm building a new database with a much smaller team of amazing engineers. And because we're building a new database, I get to rethink about a lot of those ideas, about a lot of those architectures. No need to take photos in the sense that database is not quite ready yet. You cannot go to the website and start using it. So it also means I'm not here to sell it to you because it does not quite exist yet. But it does mean that I've spent the last year and a half rethinking about how to build a modern database from first principles, looking at every bit of architecture, what works, what doesn't, in what situation. So without further ado, let's talk about those architectures. So as I mentioned before, the big problems that we're trying to solve when we talk about serverless databases is elasticity. The fact that we want to, as the vendor, it behooves us to accept every bit of workload and to make sure it works well. Otherwise, workload that we have to reject is workload we cannot charge someone for. And it means that we need to take distributed systems and make them a lot more flexible than they were before. Typically, elasticity means that things have to auto-scale. That's interesting. From 0 to basically whatever. People usually imagine that the cloud has no limits, so it behooves you to have no limits. You want to do it in small increments because people prefer to pay at small increments than I have 1 extra byte, now I have to buy this big extra machine. That's not exactly serverless. You want the resources you pay for to match what you're actually doing. It has to be almost instantaneous. It used to be that scaling, I think Aurora serverless used to take like 20 minutes until you get more resources. This thing is no longer acceptable. And it has to be in response to load and utilization, as opposed to someone clicking, I want more data button. So in order to build all that, it's a lot of difficult decisions and a lot of trade-offs. And nobody does all those 5 elasticity requirements that I mentioned. And we're going to go over some of them, those decisions, and really see how different decisions carry with them other different decisions. If you choose to be multi-tenant, there is a bunch of things you have to do. If you choose to have local storage, there's a bunch of things you have to do. And those shape the systems that you're looking at. So if you're looking at one type of database, you will see something very different because of the architecture. So the things that makes, let's say, Amazon Aurora different from CockroachDB, different from DynamoDB, very different from Snowflake, is in many ways those deep architectural decisions. So let's start with one big architecture decision, the shared nothing architecture. This should be at least slightly familiar for the reasons that this is the old school architecture. Many people would say, Gwen, this is not cloud native, or yes, some of the older cloud systems do it. It's not really that. Well, the systems that do it would be DynamoDB, Vitess, Yugabyte sitting out there. So there are Confluent, Kafka and Confluent Cloud was one of those. So there are successful systems built in this architecture, which is why I hate discounting it as not cloud native. I mean, hey, DynamoDB did it. Who knows if it's not cloud native? The way the system is built is, at the essence, you have data nodes. Data nodes own compute and local storage. This is obviously great if you believe that local storage is actually faster and more reliable than the storage clusters otherwise available. And it's obviously good as long as all the computation is local. There is a query router, usually routers, whose job is to distribute the queries and sometimes also consolidate the results. You try to minimize how much data is going in between the nodes as much as possible. You try to keep every node independent. This also means making data modeling decisions. So if you go and look at the Vitess documentations, they'll have a big section on how to model data, so it will work well in that model. Similarly for DynamoDB and other systems. Well, you have this system. How do you scale it? That's kind of what elasticity means. First of all, you need to move things in and out. All the data in each of the data nodes is in the form of small partitions. You move them around, basically. You add another node, you move partitions around. Some of the partitions become highly loaded. You try to move them to a better place. You basically, the main solution is scale those data nodes out. Obviously, you can add query routers. You can add more metadata nodes. Transaction coordinator is the one that is actually much harder to scale out in general. Usually, when those systems have scalability issues, it's because you're bottlenecking on transaction coordination in some way. Now, note that the key thing here, the ability to scale the whole thing is built on the fact that partitions are very small, and therefore you can move them around with fairly low latency, very little issues, even while the system can be quite loaded. This is how you resolve hotspots. Well, in order to keep the partitions small enough, remember, people are reading and writing data all the time. How do you keep them small? Two main techniques. One of them is that you split them. Partition got above a certain size, it now becomes two partitions. Again, very old technique. I don't think I'm saying something new here, but still used in DynamoDB. It's great if your partitioning scheme is hash partitioned or range partitions. These kind of things work quite well. The other solution is what is also known as tiering. This is what Kafka did. And the insight here is that you look at a partition and say, well, actually, only this small chunk at the top is valuable. Remember that Kafka is a log. Most of the reads and writes are on the top of the log. Like the top 10% get 90% of the load. This means that in order to keep it small, you can take the tail of the log and shove it into slower storage, like S3. And this keeps the main hot partition much smaller and allows you to move it around. Now, the other key part of the system is the rebalancing algorithms. The idea is that you have a lot of metrics about the load on the node level, the load at the partition level, and you have a process that continuously looks at all those metrics and says, oh, this node is getting a bit loaded, it doesn't have enough capacity, let's take some of the partitions and move them somewhere else where it makes sense. Or if there is no place where it makes sense and things are getting loaded, you need to actually add capacity. And those algorithms have to be, those are really challenging. I'm waving my hand, but we had a lot of smart people spend a lot of time trying to get it right, because you don't want to move data too much. It takes resources, and those resources could be better used for something else. On the other hand, you do need sufficient spare capacity on every node to allow things to burst and to give you headroom to handle all kinds of situations. So one of the things we learned is that you really want to aim at a lot of local decisions with some safeguards. You don't want to come up with this amazing global plan for the entire cluster with the perfect placement for everything, because it takes a lot of time to compute this plan. In a large cluster, it can be hours. And as a result, by the time you finished computing and finished moving everything, the situation changed. Cloud moves very fast. Workloads change all the time. So don't do that. Look for signals that things are getting highly loaded, like at the 60-ish% CPU, and start moving some things to a less loaded node. It will keep things in more or less in balance over time. Obviously, if you find out that you move things between two nodes or the same partition a lot, then you need to flag that, hey, something is off here, and maybe we're doing useless work. OK, the other big algorithm, compute storage separation. This is the one that's considered more cloud-like. The Snowflake paper, I think circa 2011, says in the cloud, the architecture that takes the best advantage of the cloud system in order to provide elasticity and flexibility for the users is the compute storage separation. Everyone looked and said, yeah, that looks like a good idea. And a lot of those architectures showed up. The main idea is that you're now running two clusters. You have a storage cluster where the data is just, think about it as dumb blocks. S3 is a good example, or even EBS. You just have chunks of data stored in there, and any machine can reach out to anywhere in the storage cluster to grab any set of blocks. And the responsibility of the storage cluster is basically don't lose blocks and be available. That's the main thing, although you can push more down into it and ask it to do a bit more. Compute nodes are the ones that do the majority of whatever you need your system to be. Filters, joins, aggregates, whatever you need from your compute layer, this is where it's happening. And the key to this system's performance is that you want things in the compute node to be logically cohesive, so you can take good advantage of caching, because remember, the storage node, you have to reach out to another cluster, and then joins require, obviously, a lot of data locality. So you are looking for ways to get everything you need for specific workload on one compute node. So if you go to, say, Snowflake, they will ask you to define multiple data warehouses. Those data warehouses are essentially compute nodes. And if you need more compute, you will buy additional data warehouses. Now, how do you scale those? There is basically two methods of scaling them. We'll start with the Aurora Snowflake type of scaling. Storage cluster is easy. It's, again, a cluster of bytes of data. You add additional nodes. They will replicate things over. Stuff will move over. It basically, in many ways, the storage cluster still acts like share nothing cluster, except it's a storage cluster. The compute nodes, on the other hand, in the Aurora model, they don't scale out. They scale up, meaning that every compute node is essentially a database. And this has amazing advantages, because it means that you can look at it like it's a normal database. You don't have to think hard about how do I partition data correctly. You don't have to think about, well, some of my data is not local, and if I have transactions, I have to do some logs, and they take extra time. You basically use it normally. If and when things get loaded, they have nice ways to take the container with the database, with its entire state, with all the connections, with all of everything, and either give it more space on the spot, which is, I think, fairly easy with modern containers, Or if the entire physical node is busy, they can move it with, should be transparent. In reality, you will see a blip in your latency graph when this happens. It's not as transparent as many want it to be. Now, with this model, it has two interesting benefits on what you get from it. One of them is that the compute storage separation means that you can do nice things like spin up another compute node and point it to the same storage and set up copy on write. This essentially just created a branch of your database. Now, Delphix, if anyone remember, did it ages ago. This is obviously much easier because you just do a click and you don't have to actually run the whole thing. It's Aurora, it runs in the cloud. So this kind of situation is kind of nice. Obviously, it has limits on how much it can scale up that are a bit harder to solve. Oh, and the other thing is that, I don't know if you guys remember, back in the day when we were all in data centers, there was this thing where everyone used those big storage clusters, like EMC and stuff. And then there was always this big Oracle database that whenever it took its weekly full backup, usually like on Friday at 3 a.m., everything else would grind to a halt. It doesn't happen quite that badly on Aurora, but you definitely sometimes notice that the storage clusters that you're on is a bit busier than normal. You see some noise from that as well. Now, the other approach to compute storage separation is the one that was started with the Spanner paper, and if CockroachDB has this kind of system, which is that you separate compute and storage, but you also scale out the compute nodes. Fantastic. But how do you maintain things like transactional integrity when you have compute nodes, every one of them handling their own workloads and their own transactions? And this is where things get pretty complex. They use things like Raft and Paxos to maintain transaction logs and maintain, you have to get consensus on transactions. So all the compute nodes, basically, the storage cluster is not just write data, it is maintain transaction guarantees, and it has to log all the transaction guarantees. Now, both Spanner and Cockroach, they're at global scale. Things like Raft and Paxos are extremely efficient in a data center. The moment you start trying to make them global, they actually lose a lot of their efficiencies. They're a bit too chatty for a lot of back and forth. In those cases, it's common to have two-phase commit to the other side of the globe. So you need to be aware that you cannot really stop doing transactions. If you're on Spanner or Cockroach, you're there because you want transaction guarantees, like most normal engineers who discovered that they actually want to know what their data is at the end of the day. But you have to remember that in this scenario, you can scale out impressively, and there will be slowdowns related to transaction if they cross the globe. So I summarized everything I said here, so I'm just going to skip it. You can refer to it once you get back home. But the big lesson is that there is no free lunch. You have to understand the trade-offs. If I go with Aurora, I have to not think about some things, I have to think about other things. Transactions are not an issue, cold start is an issue, minimum payment may be an issue. If I go with something like DynamoDB, then things are perfect, but I have a key value store. So there's all kinds of things to take into consideration and make sure that you understand what each system is actually capable of delivering. The one thing to note is that while you'll have to make trade-offs, if you decide you want a very elastic system and look at the situation, but it does not require changing the whole way you ever use the database. Meaning, if you like key value stores, there will be several for you to choose from. If you like relational, there will be a bunch. If you like specific type of relational and you're a MySQL fan, there will be. If you like Postgres, there are going to be. You don't have to change a lot about your worldview. This is not the same case if you try serverless functions, which is learn a whole new way to write code and manage code and so on, because it's I'm still trying to wrap my head around how to build functionality from a lot of small independent functions. The other thing is that every rubric has different latency trade-offs. As I said, like Aurora would have the spikes and a bit of noise. If you have the systems that move stuff around, you may notice the changes in performance as stuff moves around. The vendor may do maintenance at times. This will have an impact that you may notice in the graph. So you need to understand what you're getting, and you need to also understand your alternatives. And this is the important thing. Like, I've seen a lot of cases where people are like looking and saying, I can't use it because I cannot afford any performance spikes. And I'm like, but those performance spikes happen when we scale up, right? Which means that the machines that you already have is not big enough. What happens to you today when the machine you have is not big enough? Well, you have bad performance anyway, right? Except this one goes away after a few seconds, and the other one actually gets worse and worse and stuff queue up. I've seen situations where the performance requirements were unrealistic even for a provisioned system with the best engineers in the world trying to make it work, or was extremely cost prohibitive, and the customer was very clear that the cost is not going to work for them. So at the end of the day, the cloud is just someone else's computer. A lot of people imagine that problems will be magically solved if we move workloads to the cloud. I think a lot of cloud vendors encourage the magical thinking around it. But at the end of the day, it is computers and databases run by the best experts in the world with a lot of time and money to make it happen. And there are some things, some requirements that even the best in the world cannot really do. So think long and hard about, if I'm not using this, what will be the alternative, and will I actually get what I need in other situations? Oh, and the other thing about low latency in general, testing, and more testing. These things are dependent on the cloud vendor and the regions that you're in. If you're in US East 1, the chances of noise are a lot higher than if you are in a small cluster in the Southeast Pacifics. It obviously depends on your workload. If you are connection heavy, it will be very different than if you are doing huge computations, and if you're reading massive amounts of data, throughput, IOPS, all those things. You test, and test. You don't even know what is the low latency and how inconsistent things are until you try them out. Okay, with that in mind, all this does not matter if you don't actually need a serverless database. So let's talk about this. And I'm going to talk about a bunch of scenarios. So let's start with the easy one. You're a small company. You have one workload, and it's pretty stable. You're still not growing that much or that fast, or maybe you're growing pretty fast, but you can actually, because it's one workload, you can kind of plan a trajectory ahead. This is great. Fantastic. Life is good. Just figure out how much space you need for a one-server workload and move on with your life. Maybe put in something in your calendar once every 3 months to take a look to check if it's okay again. Some things are not broken, enjoy them. Now, as stuff gets bigger, usually you start having multiple workloads, but sometimes all of them are fine. So this is harder. You still have to understand how they interact with each other. You still have to worry about having enough space for this one crazy guy who may do something. You still have to really plan capacity. Planning capacity is harder. Tuning can be a lot harder because those workloads may actually conflict and require different things. But because they're fairly stable, it's almost a one-time investment. So you do it for every one of your workloads, and they don't change much, and you can move on with your life. This is still okay. If you have enough people to do it, your life is still fine. Where things get hairy, when you have a lot of variability. And variability can be in a day. It can be in a month. It can be this time of year when stuff starts jumping. All of those can be variability. It can be more predictable variability. It can also be very unpredictable variability. The fact is that if your workload is very variable, you need a lot of spare capacity. Otherwise, when you hit the peak, it will not work, flat and simple. And the problem with having a lot of spare capacity is that if you look at how much your company's customers pay, how much value your company derives from the database, it's actually along the lines of the average. Your customers don't get value when there is no workload, essentially. So there is a big gap. And especially this day and age, I've been through the 2000 recession, I've been through 2008 recession, and here we are today. Executives ask a lot of questions. Why we need all those databases that are only at 20% capacity? Why can't we put them all together and have something at 80% capacity? And we all know the answer, but it's in general not a conversation that is amazingly pleasant to have. And even more annoying, if it's a relatively small system, 70% spare capacity sounds like a lot, but it actually may not be that much in actual workload. It may be maybe just a few extra megabytes. So in this situation, that's where actually moving to serverless cluster from a cloud vendor is very reasonable. Why? Because that's the whole point of the serverless cost model, is that you're paying for what you use. So the executives will be happy because they're finally paying for the value delivered. You will not have to think about how to capacity plan for the peak of demands that who knows how high it will be and then get paid when you didn't plan enough. You will not have to sit through meetings of, am I provisioning too much or too little? Because honestly, who knows? How do you even know, right? So this is exactly when it makes a lot of sense to push the problem to someone else. Now, there is an even more fun situation. If you work for a place that is especially crazy, you may have a lot of workloads that are highly variable. This is true especially if you're working for a larger company, and especially if one that does good business across the globe. And then you have the peaks for the IPL in India versus Thanksgiving in the US, and all those things have to kind of come together. This is a nightmare if you're trying to manage it. I've been there a few times. It was always a gigantic headache. But if you set up a serverless system yourself, it puts you in a position where you can be your own cloud provider in a way. If instead of giving every workload its own machine, you can actually create a large cluster that those workloads can be elastic inside, it means that you can have a lot lower spare capacity, but because it's spread out across many machines, it's actually a lot more capacity in practice. 20% spare capacity on a very large cluster can be 10 and more times bigger than 70% spare capacity on a small cluster. Mathematics. It does mean that you need one of those solutions, moving stuff around or offloading things to S3 or all of the above, but it really means that you can get the benefits of all those, of this elasticity in your data center, which is extremely cool. So, to summary, basically, the more tenants you have and the more variability you have in your workloads, the more serverless would make sense for you from both economic perspective and from lack of headache perspective. You don't have to capacity plan for the unplannable is the main point here. So I know that many times people think that serverless DBs may be like, yeah, maybe in some situations. I think it may make more sense than you believe, and worthwhile checking if you could benefit from cost savings and less time spent trying to predict the future. Now, the last point is, how does function as a service fit in, and the force that it applies on a database? So serverless databases are useful even if you don't use function as a service, but if you do use function as a service, you absolutely need a serverless database. How many of you here use function as a service? Okay, there's a guy in the back. Okay, and maybe you will never need it, and I can go through this a bit fast. But the main point is that the more your workload is variable, the more risk it poses to your database. And function as a service, by definition, is the most variable workload possible. It can burst from 0 to hundreds and thousands of connections and requests per second in an eye blink. It can and has killed very large clusters because it's essentially a tool for self-DDoS is a good way to put it. It's impossible to capacity plan for something that can scale from 0 to thousands without blinking. So this is obviously a big concern. There is other concerns. There is no local state. It means that there is no connection pool. It will have to start connections. It will mean that it will have to read all the data it needs from the database as fast as possible when it starts. And obviously, people who are running it are paying for execution time, so they will get extremely upset when it takes a long time to get the data from the database to do its thing. Two common architectures for this situation. The simple one and then the one that actually works. The simple one is basically have all the functions connect directly to the database. It works. It works in some situations. The database, first of all, has to make it extremely cheap to start new connections. This is true for every serverless database out there. They add a proxy, or they make modifications to the protocol, they make modifications to the database itself. They have to make it cheap. This is important. Not true for every database that was not built to be serverless, especially if you have like MySQL, Postgres, you may know every connection is an entire process. You have to be very careful about things that show up, start a connection, run a single query, and disappear. The other situation where it makes sense, obviously the database has to be extremely elastic, because you don't know if it will be one function right now, and in 2 seconds it will be 1,000 of them. And you want it to be very close geographically to the functions. Again, not bad in the cloud if you have databases in a lot of places, but it's important because, well, again, time is money in serverless world, and getting data over larger distances take longer than getting data over shorter distances. And remember that they have no state. They're never going to cache anything, so forget about, oh, the application will cache stuff, which we all kind of gotten used to over the last, I don't know, 30 years of doing databases and backends. So the ones that I think works in more situations, even though it's a bit more effort, is to have something between those functions and the database. And this something can be a lot of things. It can be a backend, because as much as I love functions as a service, I still don't believe that our entire business logic will ever be managed in tiny independent functions out there in the cloud. I think we will always do some stuff maybe in those functions, but there will always be, most of the core business logic will be in an actual backend with actual services. Functions can connect to the backend. The backend can have stable database connections that will bring some stability to the thing. Other option is to have a proxy, which will make connections. Again, it will provide this stable connection pool. And if you can throw in a cache, so much the better, because it means that all functions don't have to wait for the database, essentially. Now, I'm putting it like as a 3-tier architecture here, partially for space and familiarity, but know that you can have as many layers of this as you want and need. So think about it like a CPU, L1 cache, L2 cache, L3 cache, all those things. Have one cache very close to the database. Have one very close to the functions. Have some logic in between. I'm hand-waving again. It's actually not trivial to manage. But again, at the very least, having one layer that is business logic, backend business logic, and caching, and provides this permanent connection pool, I think makes a lot of sense in almost every situation. So to summarize, if you're going to use serverless, dig very deeply into the architecture and the trade-offs, because not all serverless are made the same. There is higher likelihood than you think that you are going to benefit from a serverless database, because they take off a lot of the capacity planning, picking machine, tuning things, and then scale in, scale out as needed, and they can save you some money. And if you use functions as a service, for the guy out in the end, you need a serverless database, and you probably need a bunch of layers in between as well. So questions, I have time for questions. Oh, okay, I have to admit that this one, I think there's a lot of challenges in sharding your database East Coast, West Coast in general, but this one is actually fairly reasonable. DNS does allow you to have locality, and AWS does have services that tell you route connections to the lower latency location.
That means that when I do sharding, I actually try to keep the copy on both data.
That's the expensive option. Usually you say, we have some customers in the East Coast and their data is in the East Coast. Especially important if you have customers in Europe, it's really, really important for them that their data will be only in Europe. So you have to figure out, look, nothing that I said solves data locality for you, which is a lot more complex than just performance, right? Because you have regulations, where is data allowed to live, how long can you keep it in each location, and so on. Does that help?
Thank you.
Thank you.
So I'll ask a question. So you mentioned the two type of architectures, mainly two types, right? One is storage compute separation, the other is shared nothing. But I feel that maybe because both of these have some kind of storage node, right? Because in the shared nothing architecture, your computing is still a storage node.
Yeah.
So I think there's still some similarities in scaling, like the storage unit of the two type of architectures. Is that correct?
It's absolutely correct, and I think it depends. Like, there's always a lot of devil in the detail, because, for example, if you take your compute nodes, like the storage is actually EBS, well, you already have a storage cluster. It's a bit too limited. You can rarely use it as shared storage it doesn't let you share it, essentially, so you can't use it as shared storage for the entire cluster, but for the data cluster, but it is a cluster. On the other hand, and this was true, very true up to maybe a year or two ago, a lot of people, when they look at the database, they don't want to even think about, even the highest tier EBS is not the same performance as you get from local SSDs with some NVMe thrown in and all that. So in some cases, when we talk about the keeping compute and storage together, I'm mostly talking about places where you really keep them physically together on the same box, like the way we used to sell Hadoop back in the day, essentially, where you want to maximize there's a lot of benefits for bringing compute and storage together, right? Like the reading from storage, for example, is way faster, higher bandwidth, and so on. You have less bottlenecks in between, which are a lot of times a problem if you have the separation. So if you are going to put compute and storage together, put them really together, otherwise you definitely don't get the full benefits of putting them together. And if you separate them out, then you need to separate them out to storage that actually gives you the capabilities that you need. And I kind of hand wave, but it's also like there's a lot of in-betweens. So for example, Snowflake, they use S3 as their offline storage that can be shared. But the data nodes, because they are long-lasting and they don't scale out and so on, they actually store a lot of data locally. It's just that the local data, they call it cache, but it's cache sitting right there on SSDs and has more space. And the idea is that they call it cache because if you lose the entire machine, they can rehydrate. But I showed it as like either this or that, but there's actually a lot of variations in between. I have time for exactly one 3-minute question. Okay, I guess it was boring. Let's say.
Maybe I can ask another one. So do you think actually there's maybe a hybrid model of share nothing and the storage and compute separate model? Because I think some of the analytical databases now they claim that they can work with both models. I think maybe StarRock is one of those. They claim that if you want high performance, you
you need to import the data from cloud storage to their own storage. I think probably at that time they may be doing some, cloud and compute and storage bundled together. But you can also just read data remotely from a cloud storage. So what do you think about this kind of model?
No, it's fantastic. I would go as far as I say that everything there is a continuum. Like, I think there's very little in the pure coupled computer storage, and there's very little in the fully decoupled. And having more models that allow you to place yourself in this continuum, because the whole goal is to optimize performance in certain situations and to allow for scale out in other situations. So the hybrid model, which is say, okay, you have virtually unlimited storage because it's all on a big storage cluster, but you also get the performance for the high performance because you're loading things into a local machine. I think this is what almost everyone is doing behind the scenes. So for me, it's more, do you want to have this control over what you're building in, or do you prefer your vendor to more automatically do it based on what they think they're going to need, and they'll have their own cache policies. So it sounds like it may be more about control, and maybe this model gives you amazing performance for your situation, and then some people would prefer slightly less control, and it may work for them. Okay, I think we're at time. Thank you so much, everyone.